Hi, I'm Dave, KE0OG, your guide through the ARRL General Class License Manual. And today we're going to talk about Chapter 6, 6.1. This is the chapter about antennas. Antennas is a favorite topic among ham radio operators, especially in HF. We're going through Section 6.1, which has to do with antenna basics. It's an incredibly short section. It talks about elements, feed point impedance, radiation pattern, isotropic antennas, gain, and front-to-back ratio. Wow, and it just throws the definitions at you. Wouldn't it be nice to just take a couple minutes, let's just set the book quietly aside, you can come back and read it later, and talk about each of these principles, what they really are. Now, the reason I'm doing this is not because there's going to be extra material on the test, but because you really need to know this stuff when you become a ham radio operator and get your stuff up on the air. These things need to start to mean something to you. So this is just a little bit of background so that when you go back and read Section 6.1, as short as it is, you'll go, aha, I know what each and every one of those things are. So let's take a tour, and we're going to start with elements of an antenna and go on from there. Here's a look at a 2-meter antenna that I own, and I just wanted to get a good look at this so that we can talk about what elements are. Taking a little bit closer look at what we've got here, we see that we have a vertical, this is called the mast right here, and it's vertical, it's pointed straight up. Now this part of the antenna which does not radiate any energy is called the boom. Now there are 4 elements, this one, here, here, and here. Now this element right here is the driven element. Okay, and you can see a little delta match right here, and you can see the cable going down here. This is the driven element. Now what happens is that these other elements, which are called parasitic elements, pick up energy from this element and re-radiate it. Now this element right here is called the reflector, and which is slightly longer than the driven element, and these 2 elements here, which are slightly shorter than the driven element, are called directors. And the end of this is that the energy goes this way primarily. It's parallel with the surface of the earth. Now the thing to remember is that each of these are called elements. There's different kinds of elements and they do different kinds of things. This particular antenna is what we call a Yagi, and because all of the elements are pointed up and down, we say that this thing has vertical polarization. Here's another antenna on my roof. This one is called a disc cone. Okay, what we're looking at here is a disc cone antenna. It looks a little weird. Let me walk you through the elements. This is the mast, and it's attached to my roof, and it's pointed up. So we've got a pretty good idea this might be a vertically polarized antenna. Now a disc cone, this up here forms the equivalent of a disc, and you can actually make it with a disc of metal if you want it. Okay, that's the disc at the top. Now let's look for the cone. The cone is made of these elements that come down kind of at an odd shape like that. And there's several of them. You don't see them all in the photograph here. But if you were to tie them together around here, you would find that you have a cone. And yes, you could make that out of solid sheet metal. You don't need to for our purposes here. So this antenna is called a disc cone because of these things. Now, as it turns out, this little thing up here, even though it's horizontal, is a capacity hat for the antenna. This down here makes up the actual radiating part. Between the 2 of them, you end up with vertical propagation. Now, the neat thing about these antennas is that they can go over many different frequencies. In this case, the lowest frequency that it will use is 2 meters, and it goes all the way down the cone to do that. But now let's suppose I want to do this on 70 centimeters. Well, with 70 centimeters, the radiation part of it is only down to here, sort of. And this antenna, therefore, has no theoretical upper limit, but in fact just over a few octaves, and that's about it for its frequency capacity. I happen to use this antenna both for 2 meters and 70 centimeters. Okay, so it's a dual band antenna for me. It is vertically oriented. Now, you can extend this principle to very, very large antennas. You could actually make one for HF, and I've seen them. The military does that when they have to be very frequency agile. But it is a vertically polarized antenna. And yet another antenna right here, you just see the tie points for it. This is an HF antenna, a horizontal loop. Now we're looking at this funny looking thing, and I'm sorry it's so hard to see here. This is an 80-meter full wavelength horizontal loop, which means it's 80 meters long. It's a pretty long piece of wire. Now what we're looking at right here is the mast, okay, and the cable for it comes up here into the bottom of this thing, which is a balun. Okay, a balun allows us to convert from the unbalanced coax feed to a balanced antenna. And so what we see up here, these are insulators. There's another one right there. And you see the wire going this way. And it goes a full 80 meters, which is approximately 250 feet, out to 3 other poles, and then comes back over here. And because this antenna is horizontal with respect to the ground, it is a horizontally polarized antenna. Now later on you may hear something about something called NVIS, which you don't have to worry about now. It's called Near Vertical Incidence Skywave Propagation. This is a great antenna for that, and is why I built that antenna. But this just gives you an example of a horizontally polarized antenna. Before we really delve into what this figure is, let me make a note that the antenna is assumed to be along this line, in this case horizontal. To look at what polarization really means, let's take this figure from the 2010 Amateur Radio Handbook, figure 19.1, and it shows you kind of what's going on in free space when an electromagnetic wave propagates. Now, this is the starting point right here, okay, and it's going down to here, so the direction of propagation is this way, and it's going essentially at the speed of light. Now this of course is a conceptualization. We note that radio waves are disturbances in the electromagnetic field, so here's the electric part right here. Now by convention, the direction of the electric field is what determines the polarization, and we see here in this diagram that that is horizontal. Okay, now the important thing here is that this whole thing can be flipped up and turned this way to get vertical, but always note that the orientation of the electric field is what determines the polarization. Now note that this is, after all, an electromagnetic field. So there is a magnetic field also, which is 90 degrees perpendicular to the electric field. And now that brings up the question, if this is vertical and this is horizontal, all of our antennas that we talk about are usually dealing with the electric field. Almost all. Some of the antennas deal with the magnetic field, and so if a magnetically determined antenna is vertical, the actual electric field is horizontal. A little hard to keep track of. Nothing that you need to worry about for the general class exam, but I just thought I'd let you know kind of what the electric fields really look like in free space. The next thing that we have on our list is to look at feed point impedance. Now, where is the feed point on this antenna? It is right there. This is a classic dipole. This length right here is a half of a wavelength, and sometimes wavelength is expressed by the Greek letter lambda. Don't ask me why, it just is. And it's that way in engineering too. Now, the feed point impedance, we remember our Ohm's law over here, E equals IR. This is the electromotive force, or voltage, equals the intensity, or the current, times the resistance. If you play a little game with algebra, your resistance is equal to the voltage divided by the current. So resistance goes up, the voltage goes up, or the current goes down. Now, we talked about the idea of reactive loads here, meaning that the voltage and the current are not in sync. If the current is lagging the voltage, we call that an inductive load. If the current is leading the voltage, we call that a capacitive load. If the voltage and the current are completely out of phase, as they are in this particular illustration right here, then we say it's 90 degrees phase. There is no real power. There's only reactive power. There will be a lot of current in the antenna, but nothing will be radiated. Now, this picture is very theoretical, and it's misleading. Because it does not represent any real kind of antenna. In fact, the normal feed point impedance on a dipole is more on the order of 50 to 70 ohms as a general rule of thumb. And very often what we can do is just take a piece of coax up there, an ordinary piece of 50 ohm coax, and connect it right to the middle to make for a very simple antenna. Now, what really happens, let's just look at the generalization here, okay? At the very end of the antenna right here, the current has to be zero because it has no place to go. There's no more wire, so the current has to be zero. Now, if what's happening here, think of it this way, as we move in this direction, the amount of current can go up because it has places to go back and forth as the RF energy hits it here. So the current goes up, and we see that on this line. Now, to maintain an overall amount of power, we're going to have to reduce the voltage. Okay. Now, so at the very end, the antenna is trying very hard to move current, which means the voltage is up. It's not actually moving any. Now, if you look at very high voltage over very low current, that means that the input impedance at this point is theoretically infinity. Now, in actual practice, that's not true. It's less than infinity, and it is, in fact, possible to feed a dipole from its end. But we have to remember that the input impedance is very high. Now, it will be at its minimum in the middle. This theoretical zero, well, it's not actually zero. What we're finding is that this voltage here is sort of a distorted waveform, and so there's a little bit of voltage going both ways here. And so what that means is you've got some current and some voltage, and you figure it out this way right here, and you end up with your 50 to 70 ohms. For this particular dipole. Now, there are many things that affect the input impedance. The book states that a resonant antenna means that at every point in the antenna, the reactance is purely resistive, meaning no capacitance, no leading currents, and no inductance or lagging currents. Now, the only way that that can do that is if the voltage and the current are in phase with each other, which would look very differently from this. That would mean that the voltage would also follow this curve, or the current would follow this curve. Now, the impedance will change along the length of the antenna. It will still be very high at the ends and a minimum in the middle. But what's going on there is that it's purely resistive. Now, in practice, the antenna up there just sits there. What you want it to do is radiate RF energy. Okay, so you don't want to get any energy lost in heating up the antenna, which does happen a little bit, or in other inefficiencies where you reflect it back at the transmitter and it just gets dissipated as heat in your final amplifier. So that's why we look for resonant antennas. But I just wanted to explain what we meant by feed point impedance is the ratio of the voltage to the current, and really nothing more. We're going to touch on antenna patterns now a little bit. Let me tell you just really what's going on. Let's suppose we're looking at a map, and that's you right here in the center, and that's with your radio station. And you've hired a pilot who's flying an airplane, and he's going to fly this airplane around your station, okay? But he's got a little radio receiver in there. He's listening to your signal, and he's going to fly whatever path will keep that signal strength constant. So let's suppose he starts out here, and he's now going to go around you, and let's suppose that this is his flight path. Now what we're going to say here is that the antenna is omnidirectional. In other words, it's received essentially the same in all directions. And so you see a pattern that looks like this is an omnidirectional antenna, and that works in the horizontal dimension. Now let's fly a little bit different flight path. Let's suppose you have an ideal dipole, maybe a dipole mounted several hundred feet in the air, so it's free space. He's going to start out here, and he's going to fly, and he's going to find out that the signal is going down until it gets down to almost nothing, and then he'll turn away from you and fly that constant signal. Oh, he's got to come back in here to keep the signal constant. Now he's got lots of signal, so he's going to bring it out like that. Now this pattern, this figure 8 pattern, is from what we might call a bidirectional antenna. Okay, we're in the same situation here, but we've got a different kind of an antenna. Now let's suppose that our aircraft takes off from here and tries to keep that signal strength the same. And it comes down like this, and then you notice a few really funny little things down here. And there's a little bit down here with some funny stuff over here, and then back over here to the main pattern. Now this antenna clearly is directional in one direction, and that's this way. Now this right here is the back lobe. Okay, these here are called side lobes. Now you'd think, well, I want to make a perfect antenna that just cuts these out, but there's no such thing. You can't do it. There's always going to be some side lobes, and there will always be a back lobe. Now this right here, this signal strength here is less than, remember the airplane had to come in really close to where you were to get the signal strength equal to here to what it is here when he's out over here. So these signal strengths are equal along this line. Now if you take this distance and this distance right here and take the ratio of them, you have what's called the front to back ratio. Okay, and that just simply means how effective the antenna is. It's sending most of the energy in the desired direction and sends the least energy in the undesired direction. So an antenna that might have a radiation pattern like this might be a Yagi or something like that. So that tells you now in a nutshell, probably more than you wanted to know, about why these lobes are drawn the way they are. These are equal strength lobes here. So if you're over here, you can hear this guy pretty well. But if you're over here, your signal strength is greatly diminished. So if this happens to be an interfering station, and this is the station you want to get, and you steer your beam in this direction, you can cancel out that interference there. Very handy thing to know how to do. Now, the bit about the isotropic antenna, if you take just a little bit of a dot, I've got a green dot right there. A isotropic antenna acts like a point source. There's only one place where all that radiation is coming from, and of course it's omnidirectional around it, whether you're looking at it from the side or whatever. It radiates equally in all directions. Well, frankly, you can't make one because the smallest practical antenna is some part of a dipole, and dipoles are somewhat directional. Now, the reason that we use this is we say, okay, dBi, or decibels related to an isotropic antenna, would be the full power that we put in there, say 100 watts. Okay, now we're going to put a real antenna. Let's suppose that we come over here and put in a dipole antenna. Well, what we're going to find out is when we look at that radiation pattern, we've got some gain in this direction and this direction, and loss in these two directions. If you take this gain, it's about 2 dB for a dipole. So you add that to the dBi. So in this direction, it appears like you've got a stronger signal. In this direction, not. Theoretical construct only, but very useful, and you will see dBi. It's decibels related to a isotropic, non-existent, imaginary antenna. Just think imaginary for that little I in there, and that's all there is to it. So until then, this is Dave, KE0OG 73.